Hello students, welcome to the next series of questions. Today we're looking at momentum. So the question sheet, please do have a try on these three questions. Again, make sure you do your other work, these are just extra. And let's see how far we get. Question 1 states that two sumo wrestlers are in a bout. And at the start they both charge each other to grapple. In doing so they collide and become still. One sumo wrestler was travelling at 3.1 meters per second and weighed 196 kilograms. If the other was travelling at 2.5 meters per second, what was his mass? Okay, so this very first question here is basically a conservation of momentum question. We have the two wrestlers just about colliding with each other, and they sort of just become sort of stuck and they're not moving. So they are moving with some kind of velocity and then they're sort of not. So in this case, what we've got is we've got the momentum of one will equal basically the momentum of the other. So because this is a vector quantity or whatever, it really doesn't matter. We can basically say, okay, then we've got our momentums and they both collide with each other. Now, of course, one of the velocities is going to be negative, because if we've got sort of one sort of person running in this direction, which is going to be positive, a positive x, then of course you've got the other wrestler coming in that direction, which of course will be a negative x sense, because it is obviously a vector. But I'm just going to sort of, we're not going to worry about that too much. I just want to know the actual sort of mass. So momentum obviously is equal to mass of one and the velocity of the one, and the mass of the second individual and the velocity of the second individual. Basically, because we've got this sort of situation, they're both colliding, they're doing whatever. What we would have is like the initial velocity, the initial momentums would equal the sort of final momentums, and their final momentum is actually equal to 0, because they've stuck together and their velocities cancel each other out. So what we actually find is that if we just rearrange, we're looking for basically M2, could be M1, doesn't matter, but we're looking for M2, and we rearrange for that. So we've got M2 is now equal to, obviously get rid of the V2, so that's M1 V1 over V2, and we just plug in our details. So we've got 196 kilos from one multiplied by the 3.1 meters per second he runs at or jumps at, and then 2.5 meters per second for the second one, and that basically works out to be approximately 243 kilos, which is relatively believable. It's actually fairly believable, because there was the world's heaviest sumo wrestler is a chap called Konoshiki, and he weighed in at a staggering 287 kilograms. So here we go. All good. Now in question 2, what do we've got? It's a very, very good sort of example, this one. I do like this one. It says the figure below shows a ballistic pendulum. These are simple devices used to measure the speed of a bullet. A bullet of mass MB makes a complete inelastic collision with the block of wood of mass M wood. As shown in the diagram, the wood acts like a pendulum. So basically the thing gets struck by the bullet and then basically just sort of swings up a little bit. After the impact, the block swings up to a maximum height of y. In terms of y, mass of the bullet and mass of the wood, what is the initial speed v1 of the bullet? So if we take a look at the initial thing, so we've got a basically initial stage of we've got a sort of bullet flying towards some kind of block of wood, and it's going to hit that way, and then that sometime later it goes from there after it sort of hits excuse my bad drawing, but basically we've got this block of wood up like that. That's the swing, that's the height that it's moved up from there to there, so that's going to be our y height, and we've got our little bullet. If you can see that, really in my bad drawing, we've got the bullet here. Now, of course, we're at the top of the swing, so we've got energies, and we've got different kinds of energies to deal with. So we have a conservation of energy concept, and we also have the conservation of momentum concepts and things like that. So let's deal with the momentum first of all. So we've got the mass of the bullet times the velocity that we're sort of really interested in, and that is equal to the mass of the bullet plus the mass of the wood multiplied by V2, because this thing is actually moved up out of the way. Now, if we just basically make V1 what we're looking for, because that's the main thing that we're looking for here, we just rearrange, bring that one down. So therefore, what we find is that we've got V1 is now equal to MB plus MW over MB V2. So at the beginning of the second stage, after the impact, what we've got is the block swinging up and comes at rest at the height. So we've got a kinetic energy concept which starts from our block, which basically moves forward and then swings up. Okay. So if we consider the conservation of energy, basically we've got the half mass of the bullet plus the mass of the wood, because they're both embedded, multiplied by the second velocity squared of the thing, the pendulum which actually moves, and then it reaches its potential height, its full potential height of mgh basically, or mgy in this case. So we've got mass of the bullet plus the mass of the wood multiplied by g and y, because we're going for an h. We just rearrange this. As we can see, we can get rid of that one, get rid of that one. It's all rather nice. So that one goes, and basically we are left with V2 is now equal to 2gh, or square rooted. Now that's really rather nice, because then if we take a look at the top part, we're looking for V1. We've got this unknown V2, and we want to get rid of that unknown V2 in terms that we know. So we've got G and H, so we know those. That's all fantastic. So therefore, what we do is we plug basically this one in for there, and we then find, or actually sorry, into there, and then we find V1 is equal to MB plus MW all over MB square root of 2GH. And that's it. Basically, you can try and plug in numbers and what have you, but that's what we're sort of looking for here. We've got, if we consider some kind of realistic numbers, so if we've got a mass of a bullet which is about 5 grams, and we have a 2 kilogram block of wood, and the height goes up only 3 centimeters, what we actually find is that the velocities that we get, the initial velocity will be 307 meters per second, and then the second velocity will be 0.767 meters per second, which does make some really good sense when you actually see that kind of thing happening. So if you consider the initial velocity, the initial kinetic energy of the bullet hit before it hits, then using the numbers that we've just made up now, you would have about 236 joules of kinetic energy, and then afterwards the system would only have 0.589 joules, so it loses a huge amount of energy. But it doesn't, because as we know, energy does convert. But it will basically have this sort of loss of kinetic energy as it becomes potential, and a bit of sound and heat and so on and so forth. Excellent, fantastic, good stuff. And question number 3. A soccer ball has a mass of 0.40 kilograms. Initially it's moving to the left at 20 meters per second, but then it is kicked. After the kick, it is moving 45 degrees upwards and to the right with a speed of 30 meters per second. So basically what we're looking at here now is that we've got this sort of ball, and it's coming this way to begin with, and then some sort of foot. There we go. That's obviously the way that a foot looks like. It almost looks like a putting iron or whatever. There you go, studs, why not? So this person kicks the ball, and the ball then flies off at 45 degrees in that direction. So it was coming along at to the left at 20, and then it's turning to the right 30. So find the impulse of the net external force and the average net external force, assuming a collision time of 0.010 seconds. So in essence, we're looking at the concepts of a impulse and that kind of thing. So going back to my really bad drawing, so football going this way, then moves up, then gets kicked off that way. So we've got a velocity here of minus 20 meters per second. We've got a positive velocity here, 30 meters per second. That's of course assuming that x is moving from left to right. And we've got an arrow, a nice little sort of angle that this thing's going off at. And basically the nice thing with this is that we've got a cos of 45, which is equal to sine of 45, which gives us 0.707. Now let's deal with the terms of the velocities, because that's what we really want to know about. So in the initial case, we've got v1 in the x is obviously equal to minus 20 meters per second. And then v1 in the y, because it's not leaving the ground, is equal to 0 meters per second. Okay, so then if we take the consideration of afterwards, we've got v2 in the x, which is going to equal v2 in the y, and that's basically going to be 30 meters per second multiplied by the cos of the angle 45. And that gives us a nice 21.2 meters per second, so it's going off like that. The impulse in the x and the y, so imp in the x, we've got the change in momentum, which is equal to m v2x minus v1x, okay, and that's basically going to equal the mass of the ball, 40, and that's going to be 21.2 minus 20 meters per second. That equals 16.5 kilograms per meters per seconds. The impulse in the y, same kind of basis, change of momentum and so on and so forth, but this is just the case for the y. So we've got m, and we've got v2y minus v1y, which is obviously equal to 0.40 mass. Then we're going to multiply that into, so I should put that one there, 21.2 minus 0, because obviously it doesn't go in the y direction initially. So that's equal to 8.5 kilograms meters per second. Now we were given the time for the impulse as 0.010, and therefore if we want to find the average velocities in x, so we've got the average velocity in x is basically going to be equal to the impulse in x divided by the delta t. So that's going to equal the 16.5 divided by 0.010, and that equals 1650 newtons. Okay, and then we do exactly the same for the y. Average Fy is equal to the impulse in the y divided by the delta t, and that equals the where's it going again, 8.5 8.5 divided by that, and then that gives us 850 newtons, acting in the Y. And so what we've actually found in this case, we've got the average force in the Y, and we've got the average force in the X, and then basically we're looking for our average force total. So that's basically going to be, you have to excuse me, I'm forgetting all these little things, but you know what I mean, they're vectors. There we go, the total. And that would be at some angle or whatever. So the average force is equal to the square roots of both our X and Y average forces. So 1650 squared plus 850 squared square rooted. That equals 1.9 times 10 to the 3 newtons, which is rather nice. And then if we find the angle, basically we're just looking for the arctan of 850 over the 1650, which equals 27 degrees. Job done. Well, hopefully that you've enjoyed those little run-throughs. Just a few questions there to help you. The ballistic pendulum one is a particularly nice one. Excellent. Catch you later.